Hello and welcome to my channel FPL, the formal proving language. In this channel I have already started a playlist about coding in FPL and all the technical details you need to know to work with FPL. However, I realized that it is also important to provide you with the background information you need to know about why it is even important to express mathematics like this today. So I decided to start a new separate playlist. And this video is the first one in this playlist. It will be the playlist about the axiomatic method. If you have ever heard about the axiomatic method, you will probably belong to a small group of mathematicians or logicians who deal with the foundations of mathematics and consider it as their main research topic. Most mathematicians use the axiomatic method daily, implicitly without even noticing that they are applying the axiomatic method, or at least without caring about it. Douglas Hofstadter, the author of the famous bestseller Gödel, Escher, Bach, once wrote that the patterns arising in the axiomatic method are little known, little appreciated, counterintuitive, and quite filled with mystery. I would say that the whole method is little known, little appreciated, counterintuitive, and quite filled with mystery. It is because, unlike the scientific method, which is well known, appreciated, straightforward, and not at all mysterious because it is based on assumptions and experiments to support them, the axiomatic method is based on pure reasoning, and as such, it is the single other possibility for our human family to learn new things about our reality. We have only two methods, the scientific method and the axiomatic method. And the axiomatic method is far less known than the scientific method. The story of this axiomatic method is very exciting. It is more than 2000 years old story of generations of mathematicians striving to look for a precise language that would enable them to express truths about reality. It is the story of visionary ideas, big philosophical questions, and finally about many shattered dreams of mathematicians who became disillusioned because the language they had in mind, which would finally enable them to express and prove every truth about our universe, will never be invented due to some fundamental limitations of our possibilities in science and in reasoning. In this playlist, I will also discuss whether artificial intelligence could help us overcome these limitations. I will provide you with some arguments that there are limitations so fundamental that even with the help of general artificial intelligence and with the help of quantum computers, we will never be able to overcome them when using mathematics to describe our reality. So I hope you will enjoy the videos in this playlist. And if so, please give them a like, share them with others to help them out, and subscribe to my channel if you haven't already. I'm starting this video with the seemingly easy question: what is the language of mathematics? When I decided to create an artificial computer language like FPL a few years ago, I thought it was a good thing to start with a list of functional requirements for my project. So I thought that would be easy. I should pick some books on this topic, read them, and simply write down the properties of the language they identify. But to my big surprise, Every single book I took in my hands and read through it created another view on the language of mathematics. All these books and scientific papers claimed to precisely describe what the language of mathematics is and what it is not, but they differed. Man, I tell you, they differed in key areas and features. So, my original idea to simply write down a list of functional requirements for my artificial FPL language suddenly developed into a research project and ended up with a 250-page long paper you can find in my FPL repository. To illustrate what I mean, let's start with some books titled The Language of Mathematics. These books are great, but they are, in my retrospective, misleading, because in my opinion, there is no such thing as the language of mathematics. Like any other language, proof-based mathematics is evolving, and it was different 2000 years ago, 500 years ago. It was even different 100 years ago to what we today perceive to be the language of mathematics, and it will evolve in the future. Moreover, the second misleading thing about these books is that they leave you with, in my opinion, the wrong impression that they describe the language of mathematics like it was always capable of expressing true statements in some absolute sense, which is not the case, as I will show you in this video. Sorry, not in this video, but in this playlist. In this video, I will be talking about something else. So, when I pick some of these books, or when you pick some of these books claiming to deal with the language of mathematics and try to compare them to each other, you will probably quickly notice that they provide no consistent description of how this language is structured. What you see here is a table taken from my research paper on FPL that you can find on my GitHub repository. The table compares 4 sources that, despite different nomenclature, agree on only a single thing. The language of mathematics is structured into some building blocks, like definitions, different kinds of theorems. We have proofs, axioms, conjectures. But what struck me as I read these books was that not all of them recognized axioms as building blocks of mathematics. Even though axioms play a crucial role in the way we do mathematics today, 3 of 4 academic publications and books listing and explaining the building blocks of proof-based mathematics didn't count axioms as constituents of mathematical language. Consequently, these publications also differed significantly in localizing where exactly mathematical texts encode semantics. One source stated that the building blocks called definitions add new symbols and expressions to the mathematical vocabulary and fix their meaning. On the contrary, some other source stated that a deductive theory like mathematics has always to start with some undefined, primitive notions, and only axioms give meaning to these undefined notions by relating them to each other. So only the properties that undefined primitive notions have, or how they behave according to the axioms, define what they are. Another striking difference in textbooks describing the language of mathematics is the purpose of, they claim, symbolic notation in mathematics has the primary purpose. Some sources claim that the primary purpose of symbols in mathematics was to abbreviate material that would otherwise become too cumbersome to state with prose text alone. Other sources claim that the primary purpose of symbolic notation in mathematics is to manipulate them in calculations to derive logical conclusions. Maybe you will say I'm too picky because the second source I'm talking here about, I'm quoting from, talks about logical calculus, and the other deals with mathematical text per se. However, both sources claim to exactly describe and localize where proof-based mathematics encodes and the purpose of the symbolic notation. At the end of my first video in this playlist about the axiomatic method, I recommend some other books about it. Ironically, they are not titled The Language of Mathematics, but they deal with it in detail. The first book is a German book of Hoffmann, Grenzen der Mathematik, The Limits of Mathematics. If you can read German, I highly recommend it and hope you will find a translation of this book in your language. Another book is the bestseller of Douglas Hofstadter, Gödel, Escher, Bach, a popular book dealing with the axiomatic method I was already talking about. The third book is a book of Javier Fresan, which was originally published in Spanish. El Sueño de la Razón was the title. And I don't speak Spanish, so I have the book in its German translation, Logik und Paradoxien, Logic and Paradoxes. It is in fact a great book about the axiomatic method. So this is all for today's first video on the axiomatic method. I hope you enjoyed it and you are surprised, like me, that even academic publications dealing with the language of mathematics claim that they describe exactly how this language is structured and its features. However, when doing so, they end up with contradicting conclusions in key areas, like, for example, by which linguistic features the semantics of mathematics are transported, or the primary purpose of symbolic notation in mathematics. So I hope you enjoyed this video and you will come back to watch the next videos on this topic, and see you later. Bye.